we introduced the net result of the Krebs cycle. Now let's look at the Krebs cycle directly. And here we have the two carbons indicated. Carbons are indicated by these round brown spheres here. Two carbons, the acetate group attached to coenzyme A in acetyl coenzyme A. Where did those two carbons come from? They came from pyruvate. Remember, pyruvate lost one of its carbons as carbon dioxide. And the oxidation of pyruvate and this Krebs cycle is taking place in the matrix of the mitochondrion. So, acetyl coenzyme A is regenerated, coenzyme A rather, is regenerated, and these two carbons that were originally contributed by pyruvate are joined to oxaloacetate, a 4-carbon molecule, to form a 6-carbon molecule, citric acid, in the first part of the citric acid cycle, or the first part of the Krebs cycle. And now we have oxidation of this 6-carbon molecule in the next step with concomitant reduction of NAD plus to NADH. NADH acquires 2 electrons and a proton, a hydrogen ion, to form NADH. CO2 is released in the next step, and that carbon from CO2 comes from one of the carbons of citric acid, and we now have a 5-carbon molecule. So we've oxidized the 6-carbon molecule to a 5-carbon molecule and reduced NAD plus to NADH, releasing 1 CO2. Where did that carbon come from? That carbon was one of the 2 carbons that came in on coenzyme A. That is, that carbon of this carbon dioxide molecule was originally a carbon present in pyruvate. The next step, we oxidize this 5-carbon intermediate of the Krebs cycle to a 4-carbon molecule, releasing another molecule of carbon dioxide. Another carbon is released, and another molecule of NADH is produced. So we reduce NAD plus to NADH by adding 2 electrons to it, plus a proton, a hydrogen ion, and we end up with NADH. And we end up with a 4-carbon molecule. And now we have an energy production step. ATP is produced in a transformation. This 4-carbon molecule is doesn't lose a carbon anymore. It goes to another 4-carbon molecule. But in so doing, it's an exergonic reaction that allows the endergonic reaction of ATP phosphorylation to take place. So an inorganic phosphate plus ADP yields a molecule of ATP. And 1 molecule of ATP is produced for every cycle of the Krebs cycle, of the citric acid cycle. But remember, at the end of glycolysis, we had 2 pyruvates. I keep harping on that, but it's very important. So that actually there are 2 cycles of the Krebs cycle that run for every molecule of glucose oxidized, because there will be 2 acetyl coenzymes A that are run through this cycle for every molecule of glucose broken down. So here we are now at a 4-carbon molecule in which we have another oxidation reduction reaction in which FAD becomes reduced to FADH2, and we have oxidation of that 4-carbon molecule. And finally, again, we regenerate oxaloacetate at the end of the cycle and produce another molecule of NADH, reducing NAD plus by adding 2 electrons and a proton. So at the end of the Krebs cycle, then, as we go through this, in the matrix of the mitochondrion, per cycle, we've gotten 1 NADH, 2 NADHs, 3 NADHs out. We've gotten 1 FADH2 out, and we've gotten 1 ATP out per cycle of the Krebs cycle. And you might be thinking, well, wait a second, you're only getting 1 molecule of ATP out. Isn't that rather low energy yield? But the key is that we have 3 NADHs produced per cycle and 1 FADH2 per cycle. And now we're almost in a position to do some accounting. But before we do that, I want to take a little more detailed view of the Krebs cycle. And here it is now looking at the chemical formulas. So here comes acetyl coenzyme A, and these 2 carbons are the carbons that were contributed by pyruvate. And those 2 carbons are added to the this carbon of oxaloacetate. They are added to this carbon right here of oxaloacetate. So the 2 carbons from acetyl coenzyme A are right here. And then we citrate, citric acid produced by, citric acid is a 6-carbon compound, 1, 2, 3, 4, 5, 6. That is produced by joining the 2-carbon acetate group from acetyl-CoA to oxaloacetate. That now is transformed, it's isomerized into isocitrate, and then that isocitrate begins to be oxidized to alpha-ketoglutarate down here, with the loss of a carbon dioxide and a production of NADH. Alpha-ketoglutarate then is oxidized to succinyl coenzyme A. Here coenzyme A plays another role. It comes in and acts as an intermediate by joining to this carbon, to the 4th carbon of alpha-ketoglutarate, releasing the last carbon contributed by the glucose molecule as CO2. So that becomes donated there. And we have NADH produced again. And this succinyl-CoA intermediate then regenerates coenzyme A, naked coenzyme A, if you will, uncharged coenzyme A, that is ready to be charged again by an acetyl group in pyruvate oxidation in the previous steps. And so that's regenerated here. And in step 6, we use the energy of GTP dephosphorylation to phosphorylate an ADP and produce a molecule of ATP. So the energy for this reaction comes from the dephosphorylation of GTP to GDP plus an inorganic phosphate, and that inorganic phosphate then can be added to ADP to form our molecule of ATP, yielding succinate, a 4-carbon molecule, which is oxidized further to fumarate, and in so doing reduces FAD to FADH2. Water is added at this point to produce malate, and malate is oxidized to oxaloacetate with the reduction of NAD plus to NADH in the 9th step of the pathway. Look at what has happened. We have regenerated oxaloacetate. We have regenerated coenzyme A down here. And we have produced CO2, 2 molecules of CO2 per cycle. We've yielded 1, 2, 3 molecules of NADH per cycle. And we've produced 1 ATP per cycle and 1 FADH2 per cycle. So now we're ready to do a bit of accounting up to this point prior to entering the last stages of glucose, ultimately glucose oxidation, which is the electron transport chain that takes place at the membrane, the intermitochondrial membrane.